Great, thanks for coming to the first of the best paper sessions. We have two wonderful papers today. The awards will be given out at the business meeting tomorrow night, so be sure to come and see them win their plaques. And our first talk is the best full paper. It is Profit Inequalities for I.I.D Random Variables from an Unknown Distribution, and Kevin will give the talk.
And thanks to the award committee for the work that led to selecting our paper. So this is joint work with José, Correa, Dütting, who's in the audience as well, Felix, Fischer. So our work is set in the framework of optimal stopping theory. So let me introduce that first. So the general setting here, I'm gonna introduce it in an abstract way, and I will fill it with content in a second. So the general setting here is there are n entities, and the input will be a stream of information about them. So first we get some information about the first entity, then some information about the second entity, and so on. And the task is to select a single one of the entities at the time when information about it is revealed. Okay, so for instance, yeah, we first see information about x1, the first entity, and for some reason we might decide to reject it. Then we get some information about the second entity. We might reject it as well. Then we get information about the third one, and for some reason, based on the information, we might decide to select it. So now the stopping time, denoted by tau, is 3. All right, and because we can only select a single entity here, we have to automatically reject all the other ones. Thank you. Okay, thanks. All right, so the entities you can think of, either they are people who are interviewing for a position that you might want to give them, or you have one item to give away, and the entities are customers coming into your store with certain valuations. Okay, but specific theoretical problems that have been looked at are, for instance, the secretary problem and the profit inequality problem, which I will introduce now. So in the secretary problem, what's known up front is only n, so the number of entities. And the information that's learned in step I is is the relative order of the prefix seen so far. So the information learned in step I is where does the current entity xi fit into the order of the prefix. Okay, and so there's some randomness here. So the order on all the entities is uniform at random, and the performance of an algorithm is measured by the probability with which it selects the maximum entity. Okay, and as well, so that the goal is to maximize this worst case guarantee as n goes to infinity, and it's well known that the best achievable worst case guarantee is 1 over e here. Okay, then another problem that's within the setting is the one of I.I.D profit inequalities. So here known up front is n as well, and a probability distribution on the. Okay, so profit inequalities, besides n, you also know a probability distribution f on the positive real numbers, and in step I, you learn the value of ntxi. So the randomness now is that all the values xi, they're actually drawn from the distribution f, I.I.D. And the performance is measured a little different. So you compare the performance of the algorithm with the expected value that the algorithm selects with the expected value that the profit selects. So what's that? The profit sees all the realizations of the xi and just selects the maximum. So you take the ratio of that, and that's your performance guarantee. Okay, and it's known due to work by Hill and Kertz from the 80s and Correa and others from EC'19 that 0.745 is the best achievable ratio here. And we are looking at a problem that's somewhere in between the secretary problem and the I.I.D. profit inequality problem. So our problem is similar to the I.I.D. profit inequality problem in that the values are also drawn from distribution, and we're also looking at the same performance guarantee, but the distribution is hidden. So it's specified by the adversary. All right. And because this problem is somewhat like, I hope I made clear that this problem is somewhere in between the secretary problem and I.I.D. profit inequality problem. So someone would expect that the best possible guarantee is somewhere in between the two best possible guarantees for the two other problems, which is true, but it's actually more on the secretary problem side. So the best possible guarantee is the same as in the secretary problem, which is a bit surprising because one would expect, so in the for the profit inequality performance guarantee, one can also extract value from the second maximum, not just from the first maximum, right? All right, so I first want to talk about how we obtain that result. And let's start as a warm-up by how to get the lower bound, that is the algorithmic results, because we are talking about performance guarantees that are less than 1. Okay, so the theorem, more formally, we're proving is that for this unknown distribution problem, there is an algorithm with stopping time tau, such that for all distributions f, the expected value that it selects is at least 1 over e times the value of the profit. Okay, how do we get that? Fairly simply, by just running the optimal algorithm for the secretary problem. So what's that algorithm? The algorithm just observes n over e values, rounded up, takes the maximum of these values, and sets that as a threshold for accepting any value that's to come. So it will accept the first value that's larger than all the first n over e rounded up many values. Okay, so why does this algorithm achieve 1 over e, not just for the secretary problem, but also for our problem? So let's assume that the distribution is continuous for now. Now look at any set of n values that you might see. Conditioned on seeing that set, the values appear in random order, right? Now you can simply plug in the result from that's known about the secretary problem, telling you that for that particular set, you select the maximum with probability 1 over e, while the profit selects it with probability 1, so you get pointwise, you get a guarantee of 1 over e, pointwise over all sets of n values that you see. Okay, so this is how we get that result. We need to work a little harder for the other direction, that's the upper bound, the impossibility result. So the intuition is as follows. So maybe the first intuition is that you cannot beat 1 over e. That you can beat 1 over e because you can also extract value from the second maximum. But so the intuition of how we showed that upper bound is the following one. So fix some algorithm. The intuition is that since A doesn't know f, and now the adversary can design f, it can only use some ordinal information, because if it sees some value, it has no idea how large that value is compared to all the other values it could see from the support of the distribution. Okay, and now, given that, suppose we can create a setting, or suppose that most of the value, most of the utility that the algorithm can extract comes from the setting where there's one huge value, that's the largest value in the support of the distribution. It's present exactly once, and it dominates all the other values. Then, conditioned on this setting, we'll see the values in random order, and if we could extract a value that's larger than 1 over e times the value of the profit, then that would contradict the result that's known for the profits for the secretary problem. Okay, so I want to make this first bullet point here a little more precise. So what does it mean that the algorithm can only use ordinal information? So okay, so this lemma is a bit technical, but I think you will learn something from from the techniques that we're using here. So let's fix some epsilon larger than 0. So what we show is that there's an infinite subset of the natural numbers with the following property. So for all steps I, there's some probability such that whenever you see values, I values, such that the last one is the maximum, then the algorithm essentially accepts with the same probability, which is in an epsilon band around this pi. Okay, how do we establish this? So we first establish it for I equals 1. That's a fairly simple statement, right? It's just saying that the first value, right? The first value that the algorithm sees will accept with always essentially with the same probability. Okay, so we can encode the algorithm in this diagram. So on this axis we have all the natural numbers, and on this other axis we have the probability that the algorithm accepts the corresponding value. So now we can just we can subdivide this interval between 0 and 1 into slices of length 2 epsilon. And because we have infinitely many values here, of course there will be one slice in which there are also infinitely many values, right? Call this set S1. So this is the first, so this is a set that satisfies this property here for I equals 1. And now we're going to further restrict the set. So we'll build a complete graph on that set. So the set is still infinite, so our graph is also infinite, but I'm only drawing 4 nodes here. Not quite infinite. Okay, so we'll draw the complete graph on the set, and now we're going to color it. So for the colors, let's subdivide this interval between 0 and 1 again into slices of length 2 epsilon. And let's look at any edge. Okay, one of the endpoints is going to be larger, right? And now there's going to be some probability with which the algorithm accepts this larger value in the second step if in the first step it has seen the first value, the other value, right? So this probability corresponds to some color, and we're just going to color that edge with that color. And we're going to do so for every edge. And now we're going to use Ramsey's theorem, which says there exists a monochromatic infinite induced subgraph in this graph. So maybe this one. And now we know that in this infinite induced subgraph, for any edge, we have the property that we want, right? That the algorithm accepts with essentially the same probability when it sees the larger value as the second value and the smaller value as the first value. Okay, this is how we establish the property for I equals 2. For larger I, we use Ramsey's theorem on infinite hypergraphs. Okay, so given that lemma, we can actually take this support, this infinite subset here that we get, and we can build a distribution into that support so that we are in that setting that I just described. So here we have some huge value. It has some small probability, so that, I mean, it's huge, so that even though we only see it with small probability, it dominates all the utility that we can extract. But the probability is so small that if we see it once, then with high probability we don't see it another time. All right, so this is all I want to say about this problem. So what we did then was we interpolated between these two problems by moving a bit closer to the profit inequality problem by giving the algorithm more information. Okay, so we looked at the I.I.D. profit inequality problem with samples. So the algorithm is given k samples here from the distribution, additionally to the value n. And now the best possible guarantee we can achieve will be a function of the number of samples k, right? So let's look at that function actually. And the one point, so this is the number of samples, and on the other axis we have the best possible guarantee that we can achieve. So what I just showed you is this lower bound of 1 over e for 0 samples. So lower bounds are solid here. So lower bounds So what I just showed you is the upper bound, right? Because we have guarantees that are smaller than 1. What I showed you before was the lower bound. And it's straightforward to see that we can extend both of them to a little O of n samples. But then there's a sharp transition when we go to a linear number of samples. So yeah, we can actually extend by, this is actually also straightforward, to our upper bound to a linear number of samples. And then at some point, it hits this well-known upper bound by Hill and Katz, which is 0.745. That's the best value that can be achieved even if the distribution is known. Okay, but how about lower bounds? So what can we achieve? What can we achieve if we are given samples? Okay, as a warm-up, let's look at how we can achieve 1/2 with n-1 samples. Okay, so 1 over e is roughly 0.63, so we are now going to improve that value given n-1 samples. So let's look at a very simple idea. So you just take the maximum of all the samples and set it as a threshold for accepting any other value. Okay, whenever you see a value that's larger than the maximum it's larger than all the samples, then you're going to accept it. So for the analysis, yes, so what's the expected value that the algorithm extracts? So it's the sum over all steps I of the probability stopping at that step times the expected value that's extracted then, right? So the value that's extracted in any step I is at least the maximum of at least n draws from f, right? So in the first step, it would be the maximum of n draws from f. In the second step, it would be the maximum of n-1 draws from f, and so on, right? So in each case, whenever the algorithm stops in any step I, condition on that, it extracts a value of at least the value of the profit, right? And now the probability of stopping is at least 1/2, right? Because whenever the maximum of all the values, that's the nxi, and the samples is in the second half, that's in the that is within the actual values on which the algorithm can stop, then it stops. Then it stops, and the probability of the maximum being there is at least 1/2, right? Or it's 1/2. Okay, but the problem here, of course, is that, I mean, we cannot improve this 1/2. So this analysis is tight because with probability 1/2, we don't stop at all, right? If the maximum is in the samples, the maximum of all values is in the samples, then we don't stop at all. Okay, let's improve this by using more samples for now. So we're going to improve it to 1 - 1 over e using n² samples. And the idea is just to use new fresh samples in each step. Again, we're going to use, so in the first step, we're going to use just n or n-1 samples. But in the next step, we're going to throw these samples away and take new ones. Okay, and then, yeah, we always select these n-1 samples, and we take the maximum of them and set them as a threshold. Okay, now for the analysis, again, we can sum over all steps. The probability of arriving in that step is simply this expression, right? Because the probability of stopping in any step is 1 over n independently, and then the probability of accepting in any step I is, yeah, as I just said, 1 over n, right? And then what we extract is this expression, which is exactly the value of the profit, right? It's the maximum of n I.I.D. draws from the distribution. Okay, in this term, it's 1 - 1 over e. Okay, so this is how we get 1 - 1 over e using n² samples. But this is a bit wasteful because we can do the same with n-1 samples. And we do it the following way. So we keep a set of n-1 values. Initially, that's just all samples. And now at each time I, we set the maximum of that set as a threshold. But if the value is accepted, fine, game's over. If it's not, then we're going to add the value to to the set S, but we're going to throw away one value uniformly at random. So we keep size n minus 1. So the set S, we keep set S at size n minus 1. Okay. So the first algorithm that achieved 1/2 you can view as keeping all the samples in the set, right? Okay, so the lemma that we can show that even though we're not using actually fresh samples in every step, the distribution of the set as a set at any time is the distribution of n minus 1 fresh samples. And then the result just follows from the considerations we made for n square samples. All right, so what I just showed you is this point here. So we can achieve 1 minus 1 over e for given n samples. And this impossibility result that we get for n samples is ln2, so there's still a gap there. Okay, there's a straightforward extension to the, so there's also a gap here actually. There's a gap between the upper and lower bound here. And what I want to talk about last is how we actually get arbitrarily close to 0.745, which is the best value we can achieve even if we know the distribution. Okay, so this, as I said, this result from, so the algorithmic result is a result from EC'19. And the algorithm works as follows. So they define a sequence of n quantiles that's independent of f. And then when they see f, they look at these quantiles of f, and they set them as thresholds. So the sequence is fairly involved. So I'm not going to speak about it here. But our algorithm essentially does the same, but it uses the empirical distribution instead of the actual distribution. And we show that taking the empirical distribution using n square O of n square samples, where there's a constant factor that depends on the epsilon, which is how close you want to get to 0.745. So we use that empirical distribution. And then for the analysis, we use this DKW inequality to bound the error in the estimated quantile. All right, so we also get this extra data point on the top right here. Okay, so this is the full picture we get. So open problems. So obviously we'd like to close these gaps, but I want to point at two important questions, or two particularly interesting questions, I think, with respect to closing the gaps. So it would be nice to know what the best achievable guarantee is actually is when you have exactly as many samples as real values on which you can stop. Also, it would be interesting to know whether a linear number of samples suffices to get arbitrarily close to 0.745. And beyond that, one could extend to different distributions. Okay, so actually this question has been solved. So Wang showed in 2018 that in the profit inequality with different distributions, if you have just one sample from every distribution and you take the maximum of that as a threshold, this is going to give you the best possible guarantee of 1/2. But there are different extensions that haven't been looked at. So for instance, multi-item profit inequalities or profit inequalities with, or maybe then for multi-item profit inequalities, you want to add matrix constraints, for instance. Okay, thanks for your time.